Hello, my name is Thomas Purcell. I'm currently an Alexander von Humboldt Fellow at the Fritz Haber Institute in Christian Carbaño's Thermal Transport Group, and today I'll be introducing you to my poster about the acceleration of the high-throughput search for strongly anharmonic thermal insulators. Finding new thermal insulating materials is necessary for the advancement of several existing and emerging clean energy technologies. Ideally, we would find new materials with a thermal conductivity below 10 watts per meter Kelvin, while still preserving the electronic and mechanical properties necessary for any given application. In order to find these new materials, we had to develop computational workflows that start out with a set of initial input structures that can be pulled from any experimental or computational materials database and continue on until accurate thermal conductivities are calculated and then stored in a local database. These workflows are built on top of existing computational packages such as Fireworks in the Atomic Simulation Environment, or ASE, and utilize the FHI-Ames electronic structure code to calculate all total energies and atomic forces. This new framework seamlessly bridges the harmonic phonon-pi calculations with the fully anharmonic ab initio molecular dynamics runs. However, before we can fully realize these workflows, we must understand which materials are or are not anharmonic. This is because traditional ways of calculating a material's thermal conductivity are based around the Boltzmann transport equation, which assumes that the harmonic approximation is a good representation of a material's vibrational properties. If this is not the case, then a fully anharmonic ab initio molecular dynamics calculation is necessary, but the cost of this means that it's impractical to run for all materials. However, before we can actually go into determining where to make this switch between perturbative and more accurate ab initio molecular dynamics approaches, we must first understand what exactly are anharmonic effects. Traditionally, anharmonic effects are considered to be all of those that are not described by a second-order Taylor expansion of a material's true potential energy surface around some reference structure. However, because we care about vibrational properties of material, we're not going to be using the potential energy surfaces, but the atomic forces in order to measure the anharmonicity in a material. This is because the atomic forces dictate the vibrational properties, not necessarily the potential energy value itself. In order to get to our new measure of anharmonicity, or sigma A, we simply take the RMSE of the harmonic model with respect to the atomic forces and divide that by the standard deviation of all of the atomic force components at some thermodynamic equilibrium. From here, we can then see how well this new sigma A value correlates to the thermal conductivity of the material, or kappa. As you can see here, we see a very strong linear correlation on the log-log scale, implying some power law scaling. Except there are some outliers comprising mostly of half-Weisner materials, which suggests that maybe the power law isn't some constant power law scaling, but should be material specific, or perhaps subgroup discovery is necessary in order to see the various different pockets between sigma A and kappa. In order to see potentially which one of these is actually more accurate, we use the short independent screening and sparsifying operator, or SISO approach, to get better models of kappa from sigma A. This approach combines symbolic regression with compressed sensing in order to get the best low-dimensional algebraic descriptors for a given target property from a set of billions upon billions of possible input or possible features. It does this by first calculating the correlation between all your features with the target property and storing the highest correlated features in a subspace known as S1D. From here, you can trivially calculate the best 1D descriptor by taking the highest, most correlated feature. From here, you can then calculate the residual from this 1D model and use that to see which features now correlate with that residual. From here, you can store those in S2D, and when you take the union between S1D and S2D, you can then apply a sparsifying operator in order to get the best two-dimensional descriptor. This algorithm can then be repeated until you reach some cutoff value in order to get the best ND dimensional model. From here, if you look at it using only the 1 and 2D CISO descriptors, we're able to see that it is in fact you need to have a more complicated scaling law in order to describe sigma A, in order to get an accurate model of thermal conductivity from sigma A. In this case, even at the one-dimensional model, we can remove those outliers we saw previously, while this going up to a second dimension, we're able to see a tighter correlation between sigma A and kappa. This implies that we are on the right track of describing the anharmonicity of material, and this could in fact be used for a switch, as well as potentially used to describe other macroscopic thermodynamic properties. If you'd like to discuss more of that or any of the methods that I've introduced in this introduction, I'd be more than happy to talk to you at the conference. Thank you for your attention.